Hello, my name is Xavier Green, and this is my Lab 4 Oscillations for Physics 2211. The purpose of this lab is to observe the motion of a spring mass system with the mass oscillating while moving in the x and y direction. This lab incorporated the use of different softwares. Tracker software was used to track the observed position of the mass. GlowScript was used to create a computational model that predicted the motion and energy of the oscillating mass while also comparing results with the observed model. The goal is to determine if the model follows the energy principle, and the result is the system's total energy stays at a constant zero, therefore exemplifying the energy principle. The forces acting on the mass are gravity pulling downward and the spring force, which pulls towards the equilibrium position. The total energy of the system is the sum of kinetic, gravitational potential, and spring potential energy. By tracking how those energies change, we can check if energy is conserved throughout the motion. To start, I used the program Tracker to analyze a video of the spring mass system moving in 2 dimensions. I calibrated the video using the meter stick, set the origin, and tracked the center of the mass frame by frame. The video shows the mass stretching the spring as it swings like a pendulum. From Tracker, I exported the x and y position data as a CSV file, which I'll use later for the computational model. I then used Tracker data to determine the starting conditions for my simulation. The mass was 0.402 kilograms, the spring constant was 6.83 newtons per meter, the relaxed length of the spring was 0.123 meters, initial velocity is 0, and initial position is a vector negative 0.1106, negative 0.64910 meters. The initial position came from the first data point, and the initial velocity was close to 0 because the motion started near the turning point. These values were entered into GlowScript model to match the real setup. In GlowScript, I created a virtual spring mass system using the same parameters. The code initializes the position and velocity of the ball and defines the spring constant, the relaxed length, and the mass. I also imported the tracker data into arrays named x and y so I could later compare my simulation's motion to the experimental data. At this stage, the program is ready to calculate how the system evolves over time. Next, I programmed the model to calculate the spring's length and energy at every time step. The spring length vector connects the fixed point to the ball, and from that, the program finds how much the spring is stretched or compressed. Using that information, it calculates kinetic energy, gravitational potential energy, and spring potential energy, and sums them to get the total energy. Plotting these energies changes helps verify if the energy principle holds during the motion. The main loop of the program predicts the motion step by step using Newton's second law. It adds up the gravitational and spring forces to find the net force, then updates the ball's velocity and position using a small time step of 1/210 seconds. This process repeats thousands of times to simulate continuous motion. The simulation also plots x and y positions over time and compares them directly to the tracker data from the video. When I compare the simulation to the experimental data, the two motions lined up closely. Both the x and y positions followed similar oscillation patterns, showing that the computational model accurately predicts the real system. There were small differences in amplitude and timing, which could be due to air resistance, measurement noise, or slight inaccuracies in the spring constant. Overall, the model captured the key physical behavior of the motion very well. Looking at the energy plots, the total energy of the system stayed nearly constant throughout the motion. The small fluctuations are expected because of rounding and the discrete time steps used in the simulation. The energy continuously shifts between kinetic, spring potential, and gravitational potential forms, but the total stays the same. This confirms that the energy principle is satisfied for this system within the limits or measurement accuracy. Finally, I compared the oscillation periods from the tracker data in both directions. The x direction period was about 1.61 seconds, and the y direction period was about 1.52 seconds. This close agreement shows that the oscillations are coupled and that energy transfers smoothly between the vertical and horizontal motion. Any small difference likely comes from the tracking noise or the spring not being perfectly vertical. Overall, the experiment and the model confirm consistent oscillating behaviors. And then in summary, this lab demonstrated that energy conservation and Newton's laws accurately describe the motion of a two-dimensional spring mass system. The combination of tracker video analysis and glow script modeling provided strong evidence that our theoretical principles match real physical motion. Thank you.